introspection.
Hello, and welcome to the latest edition of the New Stack Demos. I'm your host, Joe Jackson, editor of the New Stack, and today we're going to be talking about the next frontier of fuzzing. This is the technique to test a program to ensure that it can manage all sorts of input without crashing or creating a security vulnerability. And today we have with us Cory Duplantis of Amazon Web Services, and he spearheaded a project called Snapchange, which is a fuzzer framework that takes the next step in the state of the art for fuzzing technologies. Welcome, Cory.
Thanks for having me.
First of all, let's talk a bit about fuzzing. Fuzzing's been around for a while, and the competitive edge seems to be the algorithms that determine what inputs to feed a program. But you're just randomly fuzzing an application won't necessarily get all the edge cases. This is where Snapchange comes in, the way I understand it, and we're just about to learn a lot more. But it is a framework. It is written in Rust for building fuzzers. This particular fuzzer is exploring a new experimental technique in which it captures memory snapshots in a KVM virtual machine. This reduces labor and supports greater introspection on the part of the developer or security pro. A snapshot is the pairing of a physical memory dump with a register state. So this gives you a lot more information about what went wrong and what other avenues to explore. So Cory, give us an example of what we're talking about here.
Sure. Yeah. So this is this example goes over uses the libtiff library as a target. libtiff is just a TIFF image file kind of program used to read and write kind of TIFF files.
Okay.
So what we can do here is what we've done prior to the demo is we've executed the TIFF info binary and then taken a copy of the physical memory from a virtual machine, and then we're replaying that physical memory over and over again in a KVM virtual machine to leverage this snapshot fuzzing technique, right? We'll get into the details in just a second. Let's get fuzzing for just a bit. So Snapchange gives us the ability to run a fuzzer via command line. There's a couple of different command line arguments that we can use. One of which, that's one of the nicer ones, is the number of cores we can use. So we can just say, let's fuzz with one core, right? So this is just doing one physical core on the machine, just having one virtual machine, loading the physical memory into that core. But Snapchange is parallelized. So we can not just do maybe one core, we can do maybe 32 cores at once. And so this will parallelize the fuzzer across 32 different cores and execute the same snapshot in each core independently of each other. And then snapshot will kind of aggregate all the information together and give you the display that we see here. So this is mostly the main view you'll see when executing Snapchange. Just kind of gives you lots of different information about the fuzzing campaign of what's going on. So for TIFF info, what's happening is we've given TIFF info just a TIFF image in memory somewhere. We know where that is. And each iteration, we are replacing that TIFF image with some other mutated image. We've replaced some bytes. We've kind of spliced some images together, lots of randomness in order to hopefully achieve try and grab crashes or corruptions and see where the edge cases are of this particular program. So what we see kind of basic statistics in the upper left-hand corner. You've got kind of the time that we've executed, the number of executions per second, just to get like an example of how performant your fuzzer is actually doing. The upper right corner is where one of the perks of this kind of technique gives us is coverage. So one of the ideas with fuzzing is we don't want to tell the fuzzer too much about the target if we can. We want it to explore the source code as best that it can by itself, and we do that via coverage. And what we do is each iteration, we capture which pieces of the code one particular mutation has seen. And if it found anything new, then we keep that input for future cases. And then in future cases, we'll take one of the kept inputs from previously and mutate that input in order to hopefully find more and more paths through the target, hopefully finding new security issues. We see like a crashes number in the upper right hand too. This is the number of supposed crashes that Snapchange has found, and a few other kind of statistics in the top portion. We get a little ASCII graph just to kind of, visually kind of see this coverage number going up to like hit our dopamine bits and, for us. We also get some performance metrics, which is really nice. So because we have real-time metrics in Snapchange, and so we can understand in real time kind of what the performance of the fuzzer itself is actually doing. And also we get some real-time coverage at the bottom too. So it's really nice as a researcher to know kind of what pieces of code we've actually done. And so we can see the symbols and the source code of the fuzzing campaign that has currently been hit. We also get the number of crashes. So we also have a tab that this is kind of a semi-bucketed list of these are the types of crashes that we see. This particular binary was executed with address sanitizer, which is a different thing, but it just captures some crashes that we normally wouldn't capture otherwise. And so this is just a list of all the directories of the bucketed kind of crashes that we've seen. And then one of the last thing that we need to do with fuzzing is not just fuzz in isolation. We want to make sure that these things actually reproduce in the real world. So if we exit the fuzzer, we can just test that our original binary does crash according to what we've seen. So we can take one of our random address sanitizer crashes with a read of supposedly 66 bytes. We'll toss one of these into our target and see that we do actually crash the target as we said he would. And so it kind of gives us that reproducibility that we do actually have a real crash from there. That's kind of the basics, like the super kind of high level of what Snapchange kind of does for the fuzzing world.
All right. So how would the developer use this information?
Yeah, so usually what happens, so the fuzzers typically make more work for us as developers or researchers. So the work that this generates is places in the code to look at to patch bugs, right? So usually when crashes like this occur, it's either a reliability issue or potentially a security issue, the stuff that I'm kind of personally caring about. And so what this is useful for is for the developer to know, hey, there could possibly be a bug here. And then you do some triage on the back end to know where exactly, what caused the crash, and can we fix it? And if we can fix it, like what's the process of getting that? So the fuzzer gives us those places to look in the code that could potentially be issues.
Nice. You said this is a fuzzer framework. So the developer has to write the fuzzer themselves, or what do you mean by framework? Or
yeah, we do. Yeah, so so Snapchange is a library that we provide various utilities for the fuzzing process. So yes, the developer does need to create a snapshot and understand at least where their data is being injected, like by a malicious actor. And then from there, we give you lots of interesting introspection capabilities. We can read and write memory pieces of that guest memory. We can access the register state. We can hook functions. We can do all these kind of introspective things that make it really nice to write fuzzers in this sort of way, just as a researcher.
All right, terrific. Can you say a bit about? So there's no commercial equivalent that AWS could go and buy off the shelf for this type of KVM type capability, I take it.
There is one other tool that's open source called What the Fuzz, oddly enough. That project in particular is kind of looking more towards the Windows side of the house. We're open sourcing this mostly for the Linux side. We've got lots of, we incorporate most of our targets are Linux based. And so most of the target process of Snapchange is for Linux things. But yeah, there's no commercial, as far as I'm aware, no commercial tool that does this sort of fuzzing methodology.
Terrific. It's good to know it's open source as well.
Yeah.
So what's the advantage of using KVM or a virtual machine rather than just running it live?
Sure. Yeah. So there's a few really neat kind of properties you get from doing snapshot fuzzing. So one of the things is pseudo-determinism. So each iteration, the same process, the same address space it is the same address space each iteration. And so we can do things like hard code addresses and know exactly the same thing is executing each time. For instance, this could be really useful for something like a race condition bug, where you might not be able to reproduce it in the real world as easy, but if you can reproduce it in the snapshot, it makes it easier to triage and kind of catch those types of bugs. We also get the ability to quickly reset the guessed memory. So usually when you're doing like a process-based fuzzing, you're going to have to either fork a process and have multiple of these going at once, which kind of has a performance penalty. Or you have to, start a process and then exit the process and start the process kind of repeatedly. In this way, we can just copy the physical memory each time, and it's a much faster kind of process.
All right, fantastic. Can you say at all what how AWS may use it in house, or if they're not using it already?
Yeah, so our team, the find and fix team, uses it as part of our analysis. So our team kind of looks at open source software, and in order to try and kind of secure open source, ideally, and so we use it heavily for our targets, and we're also kind of pushing it out for various other teams as well in AWS that could leverage this sort of snapshot fuzzing idea.
All right, fantastic. I didn't have any other questions. I don't know if there's any other aspects you want to show or anything else you want to mention.
I mean, there's tons of other things to show. That's kind of the overview, I guess, at least to see it. Yeah.
All right, fantastic. Well, Cory, thank you so much for taking time to walk us through. And this will be out so people can download the bits as of I guess. By the time this podcast goes live, this demo goes live.
As far as I'm aware, that's correct, yes.
All right, fantastic. Cory, thank you so much for getting us up to speed, and thank you, viewers, for tuning in. And we'll be back soon with another new stack demo.
Absolutely, thanks for having me.
If you like this video, please give us a thumbs up. And if you'd like to see more videos like this, you can always subscribe to our YouTube channel. We're on all the major social media platforms. You can always find us at thenewstack.io. We hope to see you soon.